Hi. If you're watching this video, hopefully you're looking to get a little bit of Regents review while the New York State Chemistry Regents still exists the way that it does. Just a quick introduction, some best practices before we get started. The number one most important thing you can have available is right here. It's a QR code that's going to point you to the New York State Chemistry reference tables. It has all of the information that you will get when you take the test, and arguably a lot of the information you're going to need to take the test. Things otherwise you might want to have, some sort of a calculator handy. And if you need a paper copy or digital copy of the Regents, there will be a link below. It is suggested that you take a look at these questions before you watch this video. It might move a little bit fast for some people, but hopefully you find this helpful, and let's get started. So for part B-1, we're still looking at multiple choice questions. There's about 20 of them. No, not about, exactly 20 of them. But the shift here is towards application, analysis, calculating answers. So if it wasn't obvious before, now we're really going to lean on our reference tables. There won't be as many of these you know it or you don't, or definition type questions. And also they don't go in the same chronological order that you might have seen in part A. We are going to start using some of these things, if you're familiar with the jargon, the science and engineering practices found in the next generation standards. For question 31, we want to know which atom has a mass of 12U. So we've been given protons, neutrons, and electrons. And really quick, if we remember, we've got a mass of 1 for the protons and neutrons, and a mass of 1 over 1836, which is essentially 0. The charges we're not going to worry about because we're only worrying about mass. So we want a mass of 12, which means we want the sum of protons and neutrons to be 12. So looking down our numbers really quickly, we've got 8, 12, 13, and 24. So our answer here is going to be 2, element E, or atom E. If we're looking for an excited state electron configuration, I look straight at the reference tables. The reference table gives the electron configuration on the bottom. This is the ground state. This is when all of the electrons have been jammed down into their lowest energy levels. They're as close to the nucleus as possible. The excited state is when one or more electrons has been given energy and it moves to a higher energy level. So what we're going to look for is 11 total electrons, which is what we have here for the atom. It does say atom. And we want a configuration that's not 281. And we also want a configuration where the numbers are shifted towards the higher energy levels. So we don't want to see like a 2-9 or something like that. 1, it's impossible. 2, that's lower energy than the ground state. So 2-8 is out. 2-8-1 is out because that's the ground state. 2-7-1 is the wrong number of electrons. This adds up to 10 total. So we're left with 2-7-2. So if we take one of these second shell electrons, bump it up to the third energy level, we would get 2-7-2, which is an excited state for sodium. We're still looking at the periodic table with these questions. The number of valence electrons in a nitrogen atom in the ground state. So again, there's our electron configuration. This is nitrogen. Don't forget, table S is still there if you need to remind yourself of which elements have which abbreviations. The valence shell is always going to be the outermost shell of any electron configuration. Looking back really quickly at sodium, the valence shell would be energy level 3, and there would be 1 valence electron. Here it's energy level 2, and there are 5 electrons found in the ground state, so the answer is 1. Graphite and diamond are both solid forms of the element carbon, which explains why you have different properties. So I copied over, I borrowed from Wikipedia some structural diamond and graphite arrangements just so you can see what they look like. Each dot here is an atom of carbon. The lines connecting them are covalent bonds. Here we've got a representation of the unit cell of the repeating structure, and here we've got some intermolecular forces holding the sheets of graphite together. So looking at these, we do see covalent bonds in both, so I don't see ionic and metallic bonding. I think that's out. I know graphite is shiny and diamond has a high boiling point, but that doesn't mean that those are those substances. So we're not looking for either of those, actually. We don't want to select 1 or 2. We've got no. This is covalent for both. Diamond has a different crystal structure than graphite. Well, that's absolutely true. Diamond has carbon atoms with more valence electrons than graphite. I didn't copy it over here, but carbon, if you look on the bottom, is 2-4. Every atom of carbon has the same number of valence electrons, so that's out too. This is a structural difference. Structure gives you function. Graphite is shiny gray. You can write with it. The sheets slide off each other, and then diamond is this hard, clear, colorless crystal. That comes from these atomic and molecular structures. Measured value for the atomic radius of platinum. So I went straight to table S and copied it. Atomic radius is found in the last column. So we're going to use 130 picometers as the accepted value. We want to calculate the percent error. Here's the formula found on table T. So the accepted value here is going to be 130 and 130. I'm going to recopy it down here to have a little bit more room and to clean it up. And really quick, grabbing my calculator. You are allowed a calculator on the Regents, non-graphing, no memory, that kind of thing. The mental math should have kicked in and it did not. But if we simplify this, we get 13 picometers over 130 picometers times 100%, and that does come out to be 10%. The picometers cancel. Percent error doesn't have a unit other than the percentage, but our answer here is going to be 10%. Be careful of this one. The 0.1 is what you get when you don't multiply by 100, so don't forget that is a step, and it is shown right there in your reference tables. Question 36. So we're coming up with a chemical formula. They've told us it's sodium oxalate. Once you see ATE in a name, that's a big indicator that you have a polyatomic ion and that you should be going straight to table E. Don't worry about memorizing at this point. Just look it up. So I've also copied over sodium. This oxidation number in the top right-hand corner is the most frequent ionic charge that you're going to get. Oxalate is shown down here. I like the swap rule. We write down both of our ions. We put the charges up top. And then we take the numerical value of the charges and we swap them. So in the case of a polyatomic ion, I usually like to put it in parentheses until I'm really sure of what I'm doing. But because this is a 1, and that 1 would distribute, but that wouldn't change anything, we're allowed to ignore the parentheses, which would give us a formula of Na2C2O4, which matches up with choice 4. What is the molecular formula of this compound? Molecular formula is just counting up what's there. So we're counting atoms. Just what is there. So I've got 1, 2, 3 carbons and 6 hydrogens, so we're just going to pick C3H6. If you were curious about the other thing that you're thinking about, maybe the empirical formula, we simplify that to simplest whole number ratios. That would be CH2, but that's not what the question's asking. A conservation of charge means that total charge of the reactants equals total charge of the products. So it's allowed to not be 0. We're showing half reactions here, so the total charge can be non-zero, but it does have to be equal on either side of this arrow. If we add these up, we get a -2, and here we get a -1. So that's not our answer. Each electron counts. These big numbers will multiply times the charge. So here we have a total charge of -4 and a charge of 0, so that one's out too. Here we have a total charge of -3 and 0, so that one's out. I really hope this one works. So 2 I minuses, that's a -2. 2 electrons and a neutral I2, that's also a -2. So our answer here is choice 2. Single replacement reactions are written in the form of A plus BC, and then you're either going to make AC plus B, or you could make BA plus C, depending on whether A is a metal or a nonmetal, or our general form is that we're looking for an element reacting with a compound to make an element and a compound. So the first choice, we've got one product. This is going to be a synthesis reaction. For the third choice, we have one reactant. That's going to be a decomposition reaction. So we'll just take those out. For this one, we have an element and a compound, and we're making a compound and an element, so that's promising. We'll check the last one to be sure. We've got a compound and a compound and a compound and a compound. Choice 4 represents a double replacement reaction. We don't want that, so our answer is, again, 2. The most polar bond. So this one I starred because it's a two-step problem. You have to not only know where to look, you also have to know what polar means, and like how it might even be more than 2 steps. So most polar bond means we're looking at electronegativity values. So we're not looking at symmetry or anything like that. Notice we've only been given one bond, so we're not looking at whole molecules if you're thinking about that. But you need to know that polarity is based off of electronegativity difference, and then you need to know to look up electronegativity on table S. Electronegativity is this fifth column here, so I only copied up to the fifth column off of table S to save a little space. We've got carbon, oxygen, hydrogen, nitrogen, and fluorine, and our values here. The difference here is 0.8, the difference here is 0. The difference here for OH is 1.2, and the difference for NH is 0.8 again. So the most polar. All right, so I'm just going to say, before I even make that distinction, even if you didn't know what you were doing, we should remove 1 and 4. So we're either looking at the largest difference or the smallest. In this case, we're going here. An FF bond is a nonpolar bond. You might want to remember that anytime that you've got two of the same element bonded, it is nonpolar. So our answer is 3. 41. Equal numbers of atoms. Equal numbers of atoms. This is Avogadros hypothesis. If your temperature and pressure are constant, then volume and number of particles are directly proportional. So we're saying number of atoms here. One of the things that's kind of hidden in here is that helium, neon, argon, and krypton are all noble gases, so they are monatomic gases, and the number of atoms is equal to the number of particles. There are no molecules here. So we're kind of like skirting around that. But what we want is same temperature, same pressure. So we're told that they're all at the same pressure. Not worried about that. So if temperature is constant, then V and N are directly proportional. I want to get rid of this neon because the temperature is not the same as the other three samples, and that's going to be a lot of calculation. I don't think it's going to be the same number of atoms as any of the other samples. So now we're looking at helium, argon, and krypton. We got 1 liter, 1 liter, 2 liters. I like helium and argon. If the temperatures are the same volume is the same number of particles. The krypton sample is twice as big. There's twice as much volume there. So there's going to be twice as many particles. Helium and argon is going to be our answer. Okay, what occurs when sodium sulfate solid is added to the system, which increases the concentration of the sulfate? So I'm going to quickly sketch the table I use to solve this. I usually write stress, response, and then I look at all the different chemicals. Now, barium sulfate is technically a solid, so we're going to be a little wonky with how we talk about that one, but the other ones we can talk about a lot more easily. The stress here is that we have increased the concentration of the sulfate ion. This means that the response is going to be to try and decrease that SO4 2- concentration, which means we're looking for this to go down. Now this is locked in a chemical reaction with the barium, so if the sulfate goes down, the barium has to go down. This should create more solid barium sulfate, and this constitutes a shift to the left. You can see that the products are decreasing, the reactants are increasing. So if we were to make like bar graphs for this, we would see the left side of the reaction, the reactants, go up and the right side go down. So let's see which answer matches up best with what we've answered here. The equilibrium shifts to the left and the barium, well, I mean, choice 1 seems to have it. Just checking, we're not doing shift right. And the barium does not increase. So yeah, the answer is choice 1. What is the name for the compound? I had to copy most of the table R for this because it was all over the place. So the names you can see are very similar with this bute, but the endings are all different. To figure out the ending, I think we're going to have to figure out what type, what class of compound we're looking at. So I've got most of table R for you here. The important part is usually the non-hydrocarbon part, and that's this here. So I want to match that up with something I'm seeing on the other table, and I think the closest one is the amides on the bottom. It's not an alcohol, which butanol would imply the alcohol. We can see that the names here have endings that give you information about the structure. What's that last one? Butanoic acid, so we're looking here. It's not an organic acid, it's not an alcohol because we've got a double bond O, knocks out the alcohol, and you've got this nitrogen here, so that really knocks out the acid. The question is amine or amide, and you can see here that the amides have this double bond O. The amines don't. So really there should be carbons on either side, which is what these R's indicate. So 4 carbons, amide, butanamide is our answer. Potential energy diagrams. What is the heat of reaction? Okay, so I know that the heat of reaction, otherwise known as delta H, is the energy of the products minus the energy of the reactants. So it's the difference between the end and the beginning. So if I were drawing some lines across, I think that's going to be 2. Yeah, I like that as an answer. Just for everyone's edification here, this is the energy of the reactants, this is the energy of the products, and this would be the activation energy of the reverse reaction if we were going from right to left. But yeah, the answer here is 2. When comparing voltaic cells and electrolytic cells, oxidation. So we've got a redox reaction going on. These are electrochemical cells, but there's another little set of words that I like to remember looking at these. Red cat and ox. And this tells you what's happening where. You have an anode and a cathode when you're looking at any electrochemical cell, whether it's electrolytic or voltaic. So here you're gonna see a both answer. But the cathode is reduction and the anode is oxidation. This little mnemonic device, this works for both. So we're looking at both of the both answers, and we want oxidation and ox. We want the anode. The answer is choice 1. Based on table J, well then let's pull up table J. Which metal is more reactive than tin, which is Sn, and less reactive than zinc, that's Zn. So it says more active, most active, and least active at the top and bottom of your table. And all we want to do is compare tin and zinc to the 4 elements that we've been given for our answer choices. And really quick, I'm just going to circle those. Only one of these answer choices is in between the 2 elements given in the question, zinc and tin. And that is our answer. We want more active than tin, so above tin, which already knocks out silver, and less active than zinc, which means you want below zinc, which knocks out cesium and manganese. The only one left is chromium, which is our answer. A titration problem. In a titration, so as soon as you see the word titration and you get numbers should really clue your brain in to look at table T. I've taken an excerpt here. This is the titration equation. Here's what all the letters mean. So really we just have to go through the problem and say, what does each thing represent? When elements start with an H, usually that means acid. When they end with an OH, that means a base, especially when we're talking about a titration equation. Sure, other compounds, that's not true. But hey, they said titration, so clue you into acids and bases. If you needed to confirm that, those are found on tables K and L. So those will pop right up for you. What is the KOH concentration? So here I have 10 milliliters. That's a volume, and since that's the acid, that's going to be VA. This is Ma. This is a monoprotic acid, so the molarity of the HCl is equal to the molarity of the H+, so that'll save us a little time there. This is the volume of the base, and they're asking about the concentration of the base. So we're just going to plug in. And I don't know how many steps you are, where you're at in your math journey, but I'm happy to show a little bit more for those who might need it. We're going to divide both sides. We're trying to isolate our MB. That's going to cancel out. The milliliters will cancel out here. So we're going to multiply and divide. You grab your calculator to do that, and you'll end up with 0.0250 molar equals MB. I don't know if it's clear. I kind of like to solve the problems before I even look at the answer choices. Sure, I can narrow them down if I'm confused, but I always like to get the right answer first instead of trying to play the guessing game. If you need to go back and look at your answers and try and evaluate those, that's still a fine choice. That's just not how I do it. Which emission causes the atomic number to decrease by 2 and the mass to decrease by 4? So the atomic number is found on the bottom. If we're looking at this AZX notation. So we want to decrease by 2 and we want to decrease by 4. So we're looking for a particle that when ejected has a mass of 2 or a mass of 4 and an atomic number of 2. So just take a look at our table, and going down the list, right up at the top, I see alpha particle is really what we're looking for. So that means that our answer is choice 1. Bright line spectrum. Don't need a reference table. Love it. All we have to do if we want to know what the unidentified element is check our lines. Now this is really going to test my ability to draw straight lines, which I don't think I have. But if we're drawing lines up, we're looking for who we overlap with. I just danced around one. That's hilarious. It looks like element L is what we're going for. Yeah, there's some closeness here for X, but we need to match every single line, and I can see that there is not anything in this 650 range for element M, X, or Z to be present, so I'm fairly confident that element L is the unidentified element just by matching things up. Okay, number 50, almost done. Which type of equation is shown? Fission versus fusion. So fission is one big element becomes two moderately sized elements, not like two very small particles. And then fusion is two or more small particles become one bigger particle. So looking here, we've got our big particle. This one neutron isn't really going to matter, and these three neutrons aren't really going to matter in terms of nuclei. We have one big becoming two smaller, and then here we've got two smaller becoming one bigger. So this tells me that equation 1 is fission, and equation 2 is fusion, which matches up with choice 3. Hope this helps. Thanks for watching.